Assalamualaikum and good evening. I bid to my lecturer, Encik Faizal bin Halim. Okay, today we would like to present on our project entitled Simulation and Design of a Plastic Injection Molding for Universal Aircond Remote Control. Before that, I want to introduce myself. My name is AMILIN HATIARA binti NORHAYAMI. For objective, the aim of this project is to show detailed steps on how to design a complete mold layout and associate component using SolidWorks Plastic 2020. This project shows a mold design process which focuses on part design, mold design, and layout drawing. For introduction, injection molding is one of the most important processes in the plastic manufacturing industry. More than 1/3 of all plastic materials are injection mold, and the mold is one of the main components in the injection molding process. The main concept of plastic molding is placing a polymer in a molten state into the mold cavity so that the polymer can take the required shape with the help of varying temperature and pressure. Injection molding is a high precision manufacturing technique that injects molten plastic into a precisely constructed mold where the plastic cools and hardens into the required component or product. The piece is then expelled from the mold either as the finished product or as a new final product that is sent on for secondary finishing. Then is product design. The product design for this project is Universal Aircond Remote Control. The function is air conditioner remote control served to achieve a specified temperature set point. It was designed using the SolidWorks Plastic 2020 software, which it is the injection molding flow simulation add-in for the SolidWorks CAD package. It also simulates the flow of the plastic melt into the mold cavity. The figure shows the 3D model for product design of Universal Aircond Remote Control with dimension of 89.13 mm x 8.02 mm x 35.17 mm. The volume of this product is 3.21 cubic centimeter. The material used in developing this product is ABS polymer. This is the design process flowchart, where it starts by insert the injection location, then it continue by insert the polymer material, then field setting setup, then run the flow simulation, then result simulation will comes up, then summary model and flow, and lastly generate report plastic simulation. Firstly is injection location. Injection location introduces polymer material at the specified melt temperature into the cavity. Point injection location was used, which position on injection location on a selected vertex or sketch point on the part. The pointer diameter that indicates the injection location was specified to 1.5 mm. Next is mesh. The plastic parts need to be meshed using shell or solid mesh. The shell analysis procedure requires a shell mesh, which is appropriate for thin wall part with uniform thickness, while the solid analysis procedure requires a solid mesh. A solid mesh is appropriate for thick parts and model with complex geometry. For this product, it using the shell mesh since it is thin wall part. Next is insert the polymer material. In SolidWorks Plastic, the material database provides access for thousands of materials suitable for plastic injection molding. For this project, the material that was used is ABS polymer. Next is insert the field setting. The field setting defines the injection molding process parameters such as filling time, melt temperature, mold temperature, and injection pressure limit. Lastly is run the simulation. After completing the input data for mesh, material, field setting, process parameter, and boundary condition, the plastic flow simulation was run.
Alright, from ZAKWAN, so I will explain and show our result simulation for plastic. Okay, first is a fill time. So the type result is minimum at 0.000150 second and at maximum 0.149865 second. Alright. So the fill time is to fill the portion inside the cavity and demonstrate how the plastic material flow to fill the mold by Wong ETAL 2004. The blue region mark the start of the front of the flow. The red region are showing the front location of the flux at a particular time interval during a filling stage animation and at the end of the fill, even though the program detects a short shoot from center blue to the end of filling road at any corner of the part. So the filling pattern is radiated. Right. So this is a fill time, and if you see red is the maximum point and the blue is minimum point from the start fill the plastic mold. Alright. Next is the pressure at end of fill. Alright, so the pressure at end of fill, the result is started at minimum 0.00000 megapascal and the maximum end at 191.302994 megapascal. Alright, so the pressure produced by the filling analysis at the end of the fill result shows that the pressurized distribution of the cavity is completed with polymer. In the fill process, a reciprocating screw controls the front injection speed. So the resulting in necessary pressure for the cavity to be filled at this speed. So the pressure of injection is propagated through the molten plastic and the result a pressure decrease spread along the flow range. Alright, so the pressure at the end of the fill is an outstanding measure of the extent of filling of the cavity. Okay, so the result the rate is the point of the gate sorry, the rate is point of the gate for the plastic, and the blue is the minimum of the pressure. Alright, so next is weight line. Alright, so the flow result, the minimum of the weight line is 1.6700 degree and the maximum is 1.9.22996 degree. Alright, so the weight line is the shear rate calculate the speed of a fluid layer that flow through an alternate layer of fluid at a different speed in contact with the cavity wall. The plastic frozen material does not move in relation to the wall, resulting in a zero shear rate at 0.01 per second. The molten plastic material just goes over a frozen material within the frozen layer, resulting in a positive rate of shear is below 0.01 per second. The shear rate increases until it reaches inside the wall. Then the shear rate begins to decrease in direction of the flow core, which reaches the local minimum. So the minimum is because in the middle of the flow chain, the polymer chain operate at the same pace and do not move in relation to one another. Alright, so if you can see, the weight line is the what I call is when the molding is flow in this if plastic is flow in the mold, so two different way is phase together. So it will come the line. It will call the weight line. Right. So next is sink mark. So the sink mark flow result started at minimum 0.002614 millimeter, and the maximum is 0.013958 millimeter. Alright, so the sink mark are depression of the surface of in an injection molded plastic part. So the biggest issue with sink marks is that there is not enough polymer molecule filled to compensate for the decrease that occur. Thickest part of the component cool at lower speed than thinner parts, leading to a major decline within the thicker section. Plastic material are insulator and thus do not transfer heat efficiently, slowing down cooling rate of thicker core volume. The longer the plastic material has to be cooled, the more the material will shrink. The high degrees of shrink pushes the surface of the part to the inner side of the core volume, causing the part to depress. Alright, so next is air trap. So the air trap result is starting at minimum 0.000150 per second and the maximum at 0.149865. So the air trap is to fill if the air in the mold cavity cannot be ventilated into the atmosphere during the filling phase. So the trapped air can avoid filling the air trap volume by the plastic content. This can lead to incomplete filling and packaging in this portion of the air trap or even a closing in the component because of the apparent air trap. So in the worst case scenario, the trapped air can be compressed, combusted and bear burn mark on the molded part. The mold core and cavity surface may damage them. It may help to reduce the incidence of air trap by inserting a split line ventilation, a spray pin, a cavity insert or a pore metal insert those places. Alright. So this is a total our analysis result in simulation plastic. So we have fill time pressure at end of mill, temperature of end, bulk temperature of end of fill, flow front temperature, temperature growth at end of fill, shear stress of end of fill, shear rate at end of fill. So volumetric shrinkage at end of fill. So the time per second of cooling time. So the temperature of end of cooling. So the vector of sink mark, velocity vector and of and attract and maximum inlet pressure, and lastly is met front flow rate. Alright, so I will continue to my team to another part. Alright, so thank you.
Okay, my name is Muhammad Sirajuddin bin HAMDZAH. Okay, my part is to explain about the drawing. Okay, this is a product drawing from isometric view for universal Aircond remote control. Okay, next, okay, this is the product drawing. I have top view, front view, side view. Okay, for the length of this product is 89.13 millimeter, and the width is 30.998, and the thickness of 7.4 for this universal Aircond remote control. Okay, next, this is a core drawing. Okay, core drawing for this model. Okay, this is a drawing. The length of this core is 200, and the width is 110 millimeter, and the thickness is 25. Okay, for this core, have many hole for the injector pin. Okay, have 16 hole for injector pin, 4 for diameter 3.9 injector pin, and 12 hole for 3 diameter 3 injector pin. Okay, for this core, have 2 product and have runner and gate, and in core also have a cooling system hole. Okay, this is a cavity drawing. Okay, cavity drawing. Okay, the dimension of cavity drawing is the length 200 mm, same as the core, and also the width is 110 mm, and the thickness is 20. At the side also have a hole for cooling system, at the center of the cavity have a diameter 12 hole to put the sprue bushing. Next. Okay. This is the mold assembly for this project. Okay, this is a mold assembly drawing. In this mold assembly drawing have left view, front view, top view, and section A. In this mold base have many components for the mold, such as the injector pin, cavity plate, core plate, locating ring, sprue, bushing, injector pin, spring, injector plate, anything else. Okay, this is the exploded view for exploded view animation. Okay. Okay, the all part is separate from a connecting locating ring, bushing, have a core plate, core cavity. Okay, next this is for open and close mold animation. Okay, mold open and close. Okay, open and close. Okay.
My name is Muhammad KHAIRI bin SHARI, and I will present about the discussion for this study. Okay, there are several defects found from the simulation. Okay, the first one is welding line defect. Welding line defect, also known as a knit line, is a flaw that happens when the plastic is injected into the mold. Since the silicone resin is injected into the container, it passes into all areas of the mold. In areas where plastic flows around a rigid piece of mold, from a plain circle to complicated form such as ring or square, the 2 or 3 strands of melted plastic fall together in one piece. The second defect is seam mark. Seam mark are depression on the surface of a plastic injection molded component. The critical explanation of the seam mark is that not enough polymer molecules have been crammed into the cavity to compensate for the shrinkage. The third defect is air trap. The air trap is the air trap within the mold cavity. It is stuck by converging silicone melt from or having escaped mold vent or mold insert, which often serve as vent. Okay, for the conclusion, the mold simulation is a vital aspect of the engineering and manufacturing of molded plastic for some purpose. Custom injection molded product should often be simulated before the prototype is made, which increases the likelihood of successful outcome. It is used as a diagnostic instrument to identify possible problems with mold flow configuration at an early stage of the process. Several issues are found from the design, which are weld line, seam mark, and air trap. The problem can be solved in many ways, such as improved design detail, proper material selection, and all. That's all. Okay, these are some recommendations to improve the plastic quality. The designers, mold makers, and manufacturing professionals must balance this variable to make quality part. First, the first variable is does the part geometry meet to draft and wall thickness requirement? Second, how long should the injection, cooling, ejection cycle be? What the optimal temperature for the material, cooling channel, and mold? Then, what's the right filling, packing pressure, and test materials to use for particular part? Lastly, will the use of special insert, side action, additional injection gates, special secondary operation, or unique cooling channel design, improve part quality, or shorten cycle time. Okay, this is the lesson learned from the study. First, the usage of SolidWorks software is really important to detect the defect during the design process. The possible failure during manufacturing process can be prevented. The third, the process to produce the draft angle during the designing is one of the struggle for this project. Then, the simulation parameter to prevent the defect also hard to be found. That's all. Thank you.